So, yeah. Having said that, let's see, is this the one? No, it's not the one. Where's it? No. These macros collide with each other, so I only open one at a time. Simulation. There we go. And the first thing you do is go to, and this is 2010, I think. Is that the version of Excel that we're working on? The latest ones is it Office 2010?
13.
13. Okay. Well, whatever this version is, you go into View and Macros and view your macros, and here you can see what macros you have labeled. And random, I'm pretty sure is that one. So if you want to see what it looks like, and we'll get into this later, you go to Edit, and that shows you your code. And this is built into all Excel. You can do your random number, or your code generation here, and your Excel, your basic program. So that's what's behind it, and we'll talk a little bit more about that next week. But if I wanted to run my program, if you'll see here, what I've done is I put in each one of these cells the value for A, for the increment, C, for my modulus, and see that's 9.12 times 10 to the 23rd. I made it really huge, that's the idea. The A and C are somewhat smaller, and then I set 653 as my seed. So then, having set those numbers, you run your macro, which what that in this case is random, and you run it, and it will test for independence. This will test for independence, and it tests for uniformity. Oh, crap there. Because what I've done here is it generates for independent and identical distributed. What is in the shaded part has to be counted. It's very legible. Let's just do it that way. What's in the shaded part here has to be counted from your current random number string. This counts the number of random numbers you generate. These are the constants that I showed you. Remember, the B matrix is constant, and also your R minus R1 minus N B1 is a constant. You just have to use them in different combinations. R2 minus N B2, R3 minus N B3. Those 6 products just recur over and over. You just multiply them in different combinations. What this does, this is our A sub I J matrix, which I typed in. There's no other way to do that, unfortunately. And then this is the A sub I J times R sub I minus N of V sub I times R of J minus N of V sub J. And what this does is it looks towards, in this case, 1 and 1 looks towards those two times each other, times that constant, so that it generates that matrix as an intermediate matrix, then adds it up, and that's our statistics right there. The statistic right there. So I have a couple, and then over here in the next area is where you test for uniformity, and I have the bins already set up all the way down to 1, and that sums it up so that we can get our chi-squared statistic for uniformity. Let me see now. So let's go to 357. One of these seeds purposefully didn't work, and that's why I put it in as an example. So let's try 357. That might be the one that doesn't work. and run a random number generator. And it's running now. It generates the random numbers, and then it will write the runs statistics right here. It's obvious that it did it. So let me do this. I'll clear those out. It went ahead and counted all those. There were 500, and I put a count. You'll notice what the count function does. It starts at 10, which is right here, and then I count it up to 2,000 so that I can generate a lot more than 500. It'll count whatever the numbers are in the cells, and I can go into the macro. And I went to edit that macro and change the upper bound. So here I set n equal 500. Let's set it equal to. Let's set it equal to 1,500. And then I'll empty this out again. And we'll run that macro again. And now it's generated 1,500, and this is our runs. But still, even 12.592 is always going to be our critical value. I've generated 1,500, and the chi-squared, the test for independence, is still less than that. So that means that that's identically and independently distributed stream of 1,500 random numbers. And that what it's calculating is the 1,500 in this column. I feel compelled to say this, and that anybody in here will do it, but a couple of years ago I had somebody that printed them out. And came with a ream of paper, and I just couldn't believe that somebody would do that. They generated 1,500 random numbers and printed them, so don't do that. None of these are intended for any kind of printing. They're just intended to use. But you can see that this is, it will generate all 1,500. And you can look at them if you want to. It's really no point in it. What's of interest is the calculations on the tests for uniformity and independence.
Can you do 500 again?
I'm sorry?
Can you do the 500 again?
Sure.
Because it looked like you did it 2 times in a row, and the R values were exactly the same both times.
They probably were because I used the same seed. They will be. As long as you use the same seed, it will be identical every time you run it.
Okay.
Yeah, that's the.
So that doesn't change like with the.
No. As long as you, until you change the seed, you will generate exactly the same stream every time.
But it's different numbers.
No, it's going to be the identical numbers because it's an algorithm. It starts with 357, and it goes through the same calculations every time, so it's the identical stream.
Oh, okay.
And that's there's an advantage and a disadvantage. The advantage is that you have to choose your A, your C, and your modulus, and your seed, so that you don't violate any of these assumptions. But if you don't violate any of those assumptions, you can reproduce your stream so that you can reproduce your experiment. It's because it's identical. And so you kind of get both ways.
So how is the seed determined then?
It's just from experience. I know that 3-digit seeds usually work pretty well. Prime numbers are good, if at all possible. And
so it really doesn't. I mean, it matters, but
yeah,
it's a random number in it.
Yeah, you can pick one and then run it and see whether or not it passes the test. Which is kind of what I do. Okay. I just know that there's, a 3-digit one that looks like it should be a prime number. Whether it is or not, I don't know, but it looks like it should be a prime number, and then I test it to see whether it passes, and it does. And that's really what counts.
And there's no such thing as more random than another one?
It's either
lower than 5.
Well, I suppose you could say that your p-value is getting larger and therefore it's better. But as long as it passes the test, that's all. It's a binary choice. Yeah. So Did you still want me to run it again, or do you?
No, that was, I just.
That was the question.
Yeah, that was the only question.
So, and then if you look over here at the test for uniformity, you can see that that, again, also is listed in the critical value, 123.225. And so it's uniform, it's independent, identically distributed, and I can do the same thing, generate another 1,500 with one of my other, let's try 719. This takes a little longer to run than others, and there we go. That's our test for identically and independently. Slightly different, but it's still less than 12.592, and the test for uniformity is still less than 123. So that is a good seed. It works fine, and we have a test of pseudo-random, 1,500 pseudo-random numbers to use. Okay. If you're going through a simulation and you're running enough, what you end up doing, what you should do, is take each random number and use it only once. Then you go to the next one. That's why you have to generate very large streams of these, because every time you use one, you then discard it and use the next one. You're not supposed to use them twice. And the reason to have a stream like this with the same seed is because then you can reproduce your experiment. I did something that I thought was kind of cool, is to generate a random walk, assuming that somebody will have a length of a walk randomly distributed and with some distribution, and a direction anywhere 360 degrees that's randomly distributed. What it would look like if you ran a bunch of these. And this is one random walk where the distance and the angle were normally distributed. Until you get to, and then you have to make a goal. And in this case, the goal was 4 units, whatever it is. So if you start out at 0, 0, this is the path, if they're both normally distributed, doing that randomly until you hit the goal of going positive 4 units. Let's see, this was normal for both of them. This was normal and exponential. It was quite short. Where the length was let's see, which one was? The length was normal and the angle was exponential. And that's what the last one of those walks looked like. It was pretty short. Exponential and uniform. That's what one of them looked like. Exponential and normal. Exponential, I'm trying to find one of them more interesting. The most interesting of all of them, I think, is the normal, uniform. There, that's a good one. Where they're both uniform. It took how many? 28,692 different legs of walking before they.
So you're never going
to. Some of them actually do go beyond the limits of Excel, but this is one that stopped before Excel got to its limit, and that's what it looked like before it got to 4.
Now, if you did this again with a different seed, you'd get something completely different.
Mm-hmm. Yeah. As a matter of fact, I ran it, I think 100 times, and every time it looks different.
You ran the simulation 100 times?
Yeah.
With a different seed or seeds?
I'm sorry?
With a different seed or the same seed? Or does this seed seed?
It's with different random numbers. The same seed, just different random number with every time
you
use one.
You made a macro for your seed to put a random seed
Mm-hmm. Yeah.
Random.
Yeah. Sometimes I got lazy with some of these. This might have been one of them. I got lazy and used Excels. because Excel does a good job of it. We can test Excel's random number generator, and it always comes out to be independent and identically distributed and uniform. So whoever wrote it knew what they were doing. And it was probably a linear congruential because they're the ones that are most common. Anyway, I thought that was, I had fun doing that one day. Now you know what I do in my free time. Don't tell anyone, right?
That's awesome.
Yeah, please. All right. So that's our pseudo-random number stream and testing it. Now let's talk a little bit about the African tanker problem, the time-driven simulation. So we have tankers arriving in the harbor every T sub 8 hours, and we can assume that that's an exponential random variable. And let's say that it's 12 hours. You have to make an assumption of 12, or an assumption of a mean, or even better, what you can do is use a mean from empirical data. That's preferable if you want your simulations to be valid. The birthing process, once again, we're assuming 3/4 to an hour and a quarter for the birthing process, and it's uniformly distributed between those two times. Loading or unloading, I said loading, doesn't matter. Whatever the tankers are loaded with requires a certain number of hours, which are uniformly distributed between from 4 to 11.5. It's a longer process. Debirthing, T sub B is exactly the same as the birthing process. And then that we have a uniform or an exponentially distributed arrival of storms that disrupt the entire process, and that the duration of them is from 2 to 6 hours uniformly distributed. You have to specify all of those, and preferably the more empirical data you have to use for your simulation, the better. If you make assumptions, it's only as good as your assumptions. This is a really good case of if you don't have good data, you'll get garbage out. It's garbage in, garbage out. I mean, you'll get great numbers, but they won't mean anything because you haven't based it on empirical data. So, how do you generate random variables of a certain distribution? This is where we make use of the uniform random numbers to generate uniform, or to generate random variables, and a variable being something different. So, if, let's just say I'm talking about the cumulative distribution function for the exponential, and I have the cumulative function, because what do I get out of that? I get a probability, right? That's what the f of x is for any distribution function. Well, the probability is between 0 and 1. That's why we're generating random numbers between 0 and 1, because that's our probability. That's our random probability. So we take our u, our random number, and set it equal to f of x. Now you can say that u equals 1 minus e to the minus x over beta, beta being the MTBF, and x being time. Well, u or 1 minus u doesn't matter, because it's randomly generated, so we might as well just call it u is equal to e to the minus x over beta. Now we solve it for, what do we solve it for? X, the time that the next one's going to arrive. We know the mean time between arrivals because we've determined it or assumed it. Determined it empirically or assumed it. We have our probability because we randomly generated that. What we're interested in is determining what the time is of the next arrival, right? So all you have to do then is set your distribution function equal to your random number, and then solve it for time, and that's the inverse, what's called an inverse transform. of your probability distribution, and that's how long it will be until the next tanker arrives, customer arrives, storm arrives, whatever. And that type of thing is usually distributed that way. So that's what the inverse transform looks like for the cumulative distribution function for the exponential distribution. For the uniform distribution, a little bit easier. Right? If this is our f of x, we solve it for x and set f of x equal to our random number. So what do? You take the lower bound, you subtract the lower bound from the upper bound and multiply it by a random number and add it back to the lower bound, and you get a time. So if u is 0.7167, let's take a look at that. And I know that my distribution of the time for birthing and debirthing is 0.75, between 0.75 and 1.25. That means that the next t sub a is going to equal to the lower bound plus the upper bound minus the lower bound times our uniform random number, which in this case is 0.7167. And assuming I did my arithmetic right, that's in the next 1.11 hours. So that's for our random, uniformly distributed occurrences. So for the exponential, what else did I have there? I think I missed something. So this is for uniform. For binomial or Bernoulli, we'll talk about that later. I don't know why I put that there. I'm sure I had something. Something's really funny out there. I take it. So this is an example of our MTBFs, anytime between failures, arrivals, whatever. And we can also do it with taking the inverse to give us lambda, so that if the average time between arrivals is 12 hours, and our uniformly distributed random number is 7167 again, then that's going to equal 4. All you do is put 12 and 0.7167 into that formula. The normal distribution, interestingly enough, is a little bit more complicated.
A quick question.
Yes.
These distributions, your uniform, exponential, and normal, are those only referring to your, in the African tanker, the 0.75 to 1.25?
Yes. Yeah,
So
that's
consider your time.
that's the time. Okay, let's go back to that one. For that particular problem, we've defined the lower bound and the upper bound of the birthing and debirthing process. If I'm doing a simulation and I'm going to try to figure out, okay, the next birthing process, when a tug goes to out to the harbor to pick up a tanker, how long will the next birthing process take?
Okay.
It's going to take 1.11. This time that's what I generated. And therefore that tug is occupied for the next 1.11 hours. Did that answer your question?
Yeah, absolutely. Yeah. But then on the next example, when you go to the exponential distribution, are we looking at that same time value but now being exponentially distributed?
No, this is 12. Remember, was the average time between arrivals for our tankers in the harbor.
Okay. Oh, I see.
So that means that I can expect for this time generation, the next tanker will arrive in 4 hours.
So we're doing it based on, I guess this is obvious, based on distribution, not based on the event.
True.
Okay.
Yeah.
All right. I was thinking about it the other way around.
Yeah. So what we're doing is we're generating the next event
Right.
by the distribution.
Okay.
Yes. I'll cut to the chase here. Probably this is what you're going to want to use, is this function in Excel, because that's going to generate the normally distributed random variable. If you put in, if you have a known mean and standard deviation, and then you put in your random number, your u sub I, it'll generate a normally distributed random number. However, historically, there's an interesting method called the polar method for generating pairs of normally distributed random numbers. First thing you do is you generate two random numbers, u sub 1 and u sub 2, let's just call it that. Then I generate two v sub I values, which is 2 times u sub 1 minus 1 for each one of my u's. And then I calculate w, it's only one w, using v1 and v2. If w is greater than 1, then I discard that and go back and start again. If w is less than 1, then I generate y, and I generate x sub I. Okay? I generate y as the first step, and that's 2 times the natural log of w divided by w, the square root of that is y. Then I generate x sub I, which is my v sub I over y. So I get 2 x sub i's. Those x sub i's are normally distributed with a mean 0, a standard deviation of 1. What does that sound like? Standard normal distribution, right? So what this gives you is two standard normally distributed random variables. So that if you want to then have something other than a standard normal distribution, which usually you do, you have to have a mean and a standard deviation from your data times that x sub I, and so that you can get your random variable. Okay, so let's take a look at an example, because I'm sure that's crystal clear. All right. So the first thing I do is I generate my u sub 1 and u sub 2. So in this case, I'm looking at these two right here. That's my first uniformly distributed random number. Okay, so then I have a v1 and a v2. Can't do it for the first row because I'm only looking at these two. So the first row is, I've thrown that out. So I generate v1 and v2, first thing I do. Then I generate my w. Okay? The w is less than 1, so I can continue. Y is 2 times the natural log of w, this number right here, divided by w, square root, and that's what I get for y. And I use my y to generate each one of the x sub i's. So I get x1 and x2. Those are uniformly distributed, those are z-scores, okay? Because those are distributions above and below the mean. They're z-scores, so you can't get negative ones. Okay? Because remember, if you go above the mean, you get positive, below the mean is negative. So, since my data are distributed with a mean of 2,500, standard deviation of 100, let's just say that that's, that's our data on time between failures. So that means that my first randomly distributed time to the next failure is 2,521.7 hours. And my next time, because we generate these in pairs, is 2,602.2 hours, based on this many standard deviations and this many standard deviations about a mean of 2,500, standard deviation of 100. Then I went to the next pair, this pair right here, I'm pretty sure. I didn't do these two, I don't think. Oh, actually I did, yeah. I did this pair, then this pair. That W didn't pass because it was greater than 1, so I had to toss that out. So then I went to this pair. That W was okay. That's my Y. My X, now that's below the mean. That's slightly above the mean, putting it into, transforming it into mean 2,500, 100. The next time between failure is 2,389.4 hours, and the next time beyond that is 2,516, and you just continue with that algorithm. It's a little bit bulky. This is what it looks like with the norm inverse function. You get just as good a stream of random variables. But the polar method is just an alternate method to generating random variables that are normally distributed. Okay. Well, it's a little bit of a tedious algorithm, but it works. Bernoulli binomial, that's really easy because you end up with if it's a Bernoulli, actually you can't really do binomials because each time you just have a probability of it occurring or probability of not occurring, and you just use the random number. Okay? So and I can use either the upper range, 1 minus my random number, or less than my random number. So the probability of failure, let's just say, I will always set the probability of failure, or the event of interest, let's put it that way, at 0.45. So if it's greater than 0.45, then it hasn't failed. If it's less than 0.45, it has failed, or succeeded, or whatever. I just set a criterion and then use that criterion and just compare my random number to that. Okay, that's my random walk, which I kind of told you about early. But this is a portrayal of what it would look like. Is you start at 0, and then you generate a leg of some distribution and an angle of some distribution. Then you have a point, and you generate a leg of some distribution and an angle of some distribution. And you continue that until you're cumulatively you're at whatever your end point is, your goal point.
Looks like a man living in a box.
I'm sorry?
Looks like a man lives in a box. Ever heard of it?
You know, I did that unconsciously. Yes, it does. In a really bad posture. We're definitely gonna we're definitely gonna injure him. So, I also set up this is something that you can solve, as we've already seen, analytically. Okay? But if we have normal, uniform, and exponentially distributed failure times for each one of the components, we can run a simulation. Let's see what my simulation looks like. There we go. So what I did is I put down I can change the hours of operation. Okay. And then I have the distribution, mean, and standard deviation for each one of the components, the maximum life if it's uniform, and the MTBF for the exponential. And I can go ahead and run an experiment. Just go ahead. It might not be very interesting because I forget it's been too long since I did this, I forget what I can erase and what I can't. So, actually, this is what I'll do. I'll run it for a different operating time, so 5,000 hours of operation. It keeps going through it through several hundred iterations so that you can collect data on how the system is behaving. 5,000 probably. Oh, did I write 1,100? Oh, okay. See, now it's iterating up from... Right.
Then we
I'm sorry?
War games, the computer's playing tic-tac-toe and it does all these.
Oh, you mean the movie?
Yeah.
Yeah.
Was Matthew Broderick?
Yes, it was. And if you'll notice what this is doing is it's incrementing this 100 hours every time. So 27, 28, 29, 3,000. And it stopped at 3,000 hours of operation. So what happened was I have 881.9 proportion, let's see, number of successes for the last run was 0 and there were 50 runs. So what I have is, what I have is for every hour of operation, I have the proportion of successes, the mean system time, that's what that was, mean system time, I forgot about that, and the standard deviation of system time to operating. And then through all my iterations down to 3,000, I have the statistics for every 100 increment. And this is a graph of the proportions of the number of hours that it operated, and this is the proportion of success. And you can see right here, this just where you would expect it, there's a precipitous drop, which that's where your analytical result will fall, is at that precipitous drop right there. So it's really, you really don't need to do a simulation on something like this because you can figure it out on your own. But it's interesting because it's an interesting exercise. That was not too interesting. That one did better elsewhere. So. Okay. Those are a couple of other questions that I posed. Okay, I think that's enough for today. And then we'll, like I said, we can do some programming next week. Oh, Linda offered that if you don't have a computer, she can check one out over at the library.
Oh.
So, if any of you need to take advantage of that, let her know. So she can bring one along. Any questions on anything before we break for the day?
Should it be pretty easy to tell which one's the proper?
Yes. Yeah. Actually, let me take a look at it, because I don't remember the homework file. It's been a whole year. I slumped off a heck of a lot of brain cells in that year, so that eats it out.
Those 2.5 minutes into our meeting.
Here's the homework. Generate a string 500. Yeah, you'll probably want to wait till next week for that. As many random variables as possible. So this one you can do by hand. And you have a stream of random numbers. So number 2 you can do by hand. If you can generate as many uniform, exponential, and normally distributed, and use the polar method for the normally distributed, just so that you can learn how to do it. So you can do number 2. Number 3 you won't be able to do. So number 2. And then we'll do, after next week we'll be able to do 1 and 3. Okay?
So just 2, not
Just
1.
2, yeah. 1 you could probably fool around with, but it would be more meaningful after next week.